А где что занято, что свободно?
Скажите, слышно?
Не, не слышно. Говорю что-нибудь. И как?
Не слышно.
Все равно не слышно? Жуть.
Хотя чуть-чуть слышно.
Не, ну сейчас слышно?
Слышно, но плохо? Что делать?
Можешь еще не сказать?
Да. Говорю. И как? Ничего не слышно? Плохо слышно?
Я считаю, что все слышно, слышно всех, кроме вас.
Сейчас, может, не той причины, можно было здесь включить.
Вот, даже меня слышно.
Камера? А, это камера, да. Микрофон с камерой считается. Если он там есть. Да.
Может, там какое-то неправильное число 13 стоит?
Вот у меня есть подозрение, что что-то начало работать. Можешь?
Что, сказать что-нибудь? А да, если слишком близко, может, говорю что-нибудь. Говорю. И как? Ничего не слышно? По-прежнему? Ничего не слышно?
Нет, слышно, но какие-то помехи.
Странно это дело. Непонятно, источник звука это микрофон или камера или что? Как бы отключили звук от камеры, по идее. Вот идет звук отсюда, но непонятно, что это за устройство. Вроде это должно быть то, что нужно.
Там нажали кнопочку.
Это должно быть этот микрофон Realtek HD Definition Audio, я не знаю.
Здесь нажали кнопочку, да?
Может, какую кнопочку нажал? Можно
Уже горит.
Power. Что еще? Может быть, вот эти децибелы неправильные? Может быть, на 0 нужно поставить децибелы? Что будет? Дай попробуем еще раз.
Ну, вообще ничего, наверное, неправильное устройство, скорее всего. То есть, может быть, дело не в микрофоне, а в том, что звук идет не от микрофона, а от камеры, если такое возможно. Или скажем, или с ноутбука, да.
То есть, ничего не изменилось?
Просто вот
Ничего не
интересно.
изменилось? Ничего не изменилось? И только хуже стало?
Да.
Нет?
Но те, кто рядом, значит, то, что, видимо, микрофон да, не подключился к ноутбуку.
Сходить с секретаршей, да?
Ну, наверное, лучше так, да.
Как-то каждый раз все по-новому.
Каждый раз.
Ну что это нужно было?
Да, это как именно трудно.
Парень говорит, причем сначала.
Они потом скучные. Не
Вообще нужно, наверное, чуть-чуть.
Все, поехал, да?
Сейчас. Может быть, вот теперь среди верхней можно
прям явно не работает.
Проверить, что все работает.
Так, трансляция у вас уже есть, да? Все, да?
Ничего не слышно? Ничего не слышно?
Подождите, сейчас. Ну,
Ничего не
у
слышно?
вас есть звук?
Да, у тебя с какого сорта
Потому что звук должен быть.
задача?
Да.
Через отход.
Ничего не слышно? Ничего не слышно?
У меня есть подозрение, что прямо сейчас, ровно в этот момент, прямо под нами, прямо в аудитории под нами Владимир Жгун разбирает полностью работающую камеру.
А нет, он уже принес
Трансляцию
ее.
на предыдущей паре.
Нет, она даже уже лежит в учебной части.
Да?
Она ее принесла.
Могу принести?
Так, не надо ничего приносить. А почему не
Не, наверное,
Ну, сейчас звук не такой плохой.
Вот сейчас?
Просто всех тоже слышит.
Так, а у вас включен?
Да, что у меня включено.
Есть.
Что-то всех слышно.
То есть звук где-то не с петлички,
Там
а
же
уже
Децибел.
Не-не-не, там ничего не надо менять.
Там был минус 30 децибел.
Просто надо понять, откуда. А здесь вот все включили?
Нет, я не контролирую процесс.
А вот сейчас все должно заработать. Надо до конца. Ну, даже не включен был.
Слышно? Сейчас слышно? Все равно не слышно? Теперь слышно? Здорово. А что, просто я плохо вставил что-то, да? Ой-ой-ой. Прошу прощения.
Все, да?
Да, спасибо большое. Okay. So last time we started proving the following theorem with a long statement. So I have to repeat it. Again, we have a coherent sheaf on a relative projective space, which projects to the base scheme S. And then the first statement is that the set of all possible Hilbert polynomials of the fibers is finite. This set of polynomials is finite. And also say the set I. For any polynomial in this set, there exists a locally closed subscheme SF in the ambient scheme S, such that first, for any well, the set of all fibers with the Hilbert polynomial equal to this particular polynomial, this set is just the set of closed points of this locally closed subscheme. In particular, the union over all f in our finite set of Hilbert polynomials of the supports of those subschemes is just the set of closed points of our scheme S. And the second universality property that we define S prime as the disjoint union of those locally closed subschemes. And then it has a structure morphism I to this scheme S. And this structure morphism has universal flattening property. Oops. That if we have any test scheme T over S, such that the pullback of F, so it's a coherent sheaf on the projective, relative projective space over T, is flat over T. Then phi factors through I. Okay, so for this reason it's called flattening, and in fact it's if and only if how to say this is flat over OT. Maybe I should say if and only if phi factors through I. And there is also the third property that we discussed last time, that the set I is totally ordered by f bigger than g, meaning that f of r is bigger than g of r for big enough r. And we discussed last time that it's due to finiteness of I. Since the degrees of all those polynomials are at most n, where n is dimension of the project space, and under this total order, the closure of the stratum SF lies in the union of S G for G bigger than F. Okay, so this was the long statement, and last time we started the proof, and what we achieved was sort of the basic case when n equals 0, so there is no projective space, there is just a sheaf F on the base S, and then we proved those statements. And also we proved 3 more claims. so I will formulate them and then we'll start using them and finish the proof of the theorem. So the first statement is the finiteness.
Could you repeat what is I? Statement I.
What is statement I? That
The set of
so if we fix some Hilbert polynomial, there are finitely many polynomials, and if we fix one of them, then all the points in S having this Hilbert polynomial of fiber form a locally, well, the set of closed points of a locally closed subscheme. So, yeah, we discussed this already last time. So it cannot be something like a plane where you remove a line but add the origin. So this is not allowed. This is not the set of points of a locally closed subscheme. It's a constructible subset.
You express the fact that it is locally closed subscheme by saying that it is a set of closed points.
Yeah, and yes, absolutely. And what else could I say?
Why it is equivalent
To what?
to say that it is locally closed subscheme and write that it is a set of closed points of this SF. Or it is trivial.
It's like on the maximum idea.
Well, I say yeah, that for any polynomial, there is a locally closed subscheme SF such that the set of fibers with this Hilbert polynomial is the set of locally closed points of this locally closed subscheme. That's what's written here. Right? Okay. So, this part A is that again, it's essentially this point 1. So there are finitely many subschemes Vi in S such that the Hilbert polynomial chi well, is equal to Fi for S in Vi. Then the second part statement followed from Grothendieck theory, namely that there exists a big enough integer such that if we twist our sheaf F by a twist high enough, then this vanishes. So for any positive R and any M bigger than N1. Okay, and also the same is true for cohomology of fibers. Okay, and finally, the property C was that for even bigger twist, we have the base change. So the higher cohomology vanish, but if we are interested in the direct image, the zero direct image, then its fiber over S will be just the zeroth cohomology of of the fiber with coefficients in the twisted sheaf. And again for any m bigger than capital N. Okay, so that's what we established last time, and now we will deduce the theorem. Yes? No, for N1 there are no higher direct images, and for still bigger N, there is base change isomorphism. So the fibers of the direct image are cohomology of fibers.
Once again, regarding the initial statement, I think we only consider somehow only closed points as.
Yes, yes. So this is notation for closed points.
Yeah, I understand. And what about the non-closed points? In principle, we could also take the Hilbert polynomials.
Yes, certainly, yes. But well, it will be equal to the Hilbert polynomial of a typical point. So if you have a non-closed point, then it corresponds to some closed subscheme, and then it's generic point of some closed subscheme. And then if you take a general point in this closed subscheme, then by the previous claim, there will be some open stratum, so there will be some typical Hilbert polynomial. It can jump under degeneration, but typically it will be always the same, and this will be the value of the generic point Hilbert polynomial there. So it doesn't say anything new. You can consider also non-closed points, but it will give no new information.
So in principle, we could erase this taking closed points and consider closed points.
Yeah, if you insist, yeah. Mm-hmm. Okay, so now let's prove our theorem. To this end, so the key thing is that we already proved it for n equals 0, and now we will reduce to n equals 0. So instead, our sheaf F on the projective relative projective space over S, we will consider its direct images, twisted direct images, as sheaves on S, and then we will rewrite everything in terms of them. So, namely, we'll consider EI like this, and EI is just the direct image of F twisted by n plus I. Okay, so there is this big number n, such that for bigger twists, everything is absolutely perfect. No higher cohomology, zeroth cohomology commutes with base change, and we consider these guys, but only for I equals from 0 to n, the dimension of the ambient projective space. So there are just n plus 1 such sheaves. Okay, now let's apply the n equals 0 case we already know to the first one, E0, and then we obtain a stratification by locally closed subschemes. Like this. Yes. Yes. This M capital. Yes, absolutely.
What is group A says? Right hand side is some Fi.
Yes. There are finitely many polynomials, Hilbert polynomials. Among all the possible Hilbert polynomials of fibers, there are only finitely many that actually occur. some finiteness statement. We proved. So if we restrict our attention just to the zeroth guy here, we obtain the stratification from n equals 0 case. And here the polynomials are just positive integers. Right? Just the ranks of fibers. And we know that if we have any test scheme from T to S, then the pullback of E0 is locally free of rank E0 if and only if gamma factors through this stratum, locally closed subscheme WE0. Okay, that's just what we proved for n equals 0 already. That's fine. And now let's somehow subdivide this partition according to the similar stratification with respect to E1, and then E2, and E3, and so on. But there are finitely many, so n plus 1 altogether. For any stratum, well, W E0, take stratification W E0 is the union over all possible E1s, W E0 E1 with respect to the ranks of fibers of epsilon 1. Okay, and so on. Well, so n plus 1 steps altogether. So we obtain the total stratification. S is the union over all n plus 1 tuples. Like this. Well, again. Now, unfortunately, I have to erase the statement of the theorem, and I will never ever repeat it. So take the last glance. So far, I don't need any order at all. Just I fix the rank of the E0, then rank of E1, rank of En. And they're arbitrary integers, but there are only finitely many that actually occur. I mean, almost all the strata are empty. There is only finitely many n plus 1 tuples which actually contribute. Right?
So we just subdivide.
Yeah, we subdivide. First, we have stratification by W E0. Then we subdivide each of them by W E0 E1. Then we subdivide each of them by W E0 E1 E2, and so on.
Я не понимаю, W E0 это одно множество или много?
Well, E0 is a positive integer. So there is W0, there is W1, W2, and so on, W1000, but everything else is empty. Yeah, there are, in reality, for this particular sheaf F, there are only finitely many strata like this. And then I start subdividing each of them into similar strata for the ranks of E1. And again, there are only finitely many in this subdivision. So there is W01 and so on, but nobody can see, well, I mean, among the YouTube watchers, nobody can see what we're doing now. Okay, so there are these strata, and then what is the bottom line? Is that there is a finite stratification W is 0 and so on, En. Such that for any test scheme over S, the ranks of pullback of EI equals small ei, if and only if gamma factors through this stratum. And here for any I from 0 to n. Okay, so that's what we achieved. And now, why did we try to achieve this? Just because, again, the degree of our Hilbert polynomials is at most n, because it's in the n-dimensional space. And so there is a bijection between such polynomials and just n to the power n plus 1, namely f goes to the collection f of n, f of n plus 1, and so on, f of n plus capital N plus small n. Yeah. So actually, the ranks of just those direct images determine all the other direct images, right? Because it's the n plus 1 tuple, and you know polynomial degree n just from this.
This is because B and C?
Yeah. You also use that there is no higher cohomology, so.
So it's just global section.
Yes. So the Euler heuristic is just global section.
And why have we made base change in this case?
Because we measure our Hilbert polynomials by this, by definition, the Euler heuristic of fibers. On the other hand, what we do know is that there
and this is the rank.
behavior of yes, absolutely. The rank of this equals the dimension of that, certainly. I mean, granted that they are locally free, if you know this, then certainly the dimension of any fiber is just the rank of this locally free sheaf. Okay, so in a sense, this is our coordinate system for such polynomials. Okay, and so we can re-denote W E0 and so on En by WF, because the information contained in F and in this n tuple is just the same. And now we're almost done. Somehow this is the desired stratification, but not quite. Just we'll see in a moment. So what do we know? That that the desired subscheme, well, locally closed subscheme S F, we just had it at the very same place before I erased it, will be a locally closed subscheme of WF, and with the same support. So the set of closed points will be the same. But maybe we'll have to kill some nilpotents.
Kill all the nilpotents or just some of them?
Some. Because I need some universality property, I erased. And because of this universality property, I cannot just kill all the nilpotents. So the problem is, I will formulate it in a moment, just what we discussed a couple of weeks ago, that for algebraic varieties, that is without nilpotents, there is a very simple criterion of local freeness that of a coherent sheaf, that all the fibers have the same dimension. But unfortunately, it does not work for schemes with nilpotents, as we discussed for dual numbers. Yeah, for example, well, we can have just a module K, and then certainly there is just one point, yeah, in this dual number. The spectrum consists of just one point, but with nilpotents. And the dimension of fiber over this point is 1, and there is nothing to compare it with, but still the sheaf is not locally free, clearly. So this criterion fails for arbitrary schemes. And just that's the only thing we have to do. So for example, in this particular case, this is our W, and the reduced point will be S. This will be a closed subscheme in W, but with the same support.
Just spectrum of K.
Yeah, in this example, yeah, S will be just the spectrum of K. So we need our sheaf to be actually locally free. Okay, so we know that all the fibers of the direct image have rank f of n plus I over WF, but this does not guarantee that this direct image is locally free of rank f of n plus I if W f has nilpotents. And so we have to kill some of the nilpotents. So there is a closed subscheme WFI in WF such that they have the same support but for any test scheme, the pullback of our direct image is locally free of rank f of n plus I if and only if gamma factors through sorry, not gamma, but yeah, gamma factors through this subscheme. Okay, and maybe let us not prove this. So, as I mentioned, this is one of the very few points where the argument for varieties does not work for schemes, but let's just assume this. And this subscheme is given by some ideal. So I in the structure sheaf. Okay. And now note that, pardon me? Note that here I is arbitrary, not from 0 to n. Yeah, so this can be erased.
Argument that if our scheme has an importance,
Yes. Yeah.
then we cannot argue that our shield is locally free.
Yeah. Just because there are too few points. Yeah. For example, we can just have one point, and there is nothing to check, nothing to compare with. Just one point. You cannot ask that the rank at this point is equal to something else. Nothing to compare with. But still, there are many nilpotent schemes, and there are many sheaves, like just modules of this nilpotent algebra, and they are not locally free. They are locally free over some quotient, and there is some universal quotient with this property.
For example, what this.
Yeah.
In this example, the structure sheaf has an importance.
Yes, certainly, for dual numbers.
And
So the algebra is two-dimensional. It is a two-dimensional algebra. It has one-dimensional module. Certainly, it's not locally free. It has dimension 1, the algebra has dimension 2. Right? So it's not locally free. But if you quotient out the nilpotent, then you get the ground field, and over it, your sheaf is locally free. It's just a vector space, one-dimensional vector space over the ground field.
What I mean by it is not locally free. So
Over the whole algebra, it is not locally free because the algebra is two-dimensional and the model is one-dimensional. Over the ground field, I mean.
So you're taking this constant shift?
I wouldn't call it constant, rather.
Okay, of dimension 1.
Yeah.
It is not free.
It's not free, yeah, and not locally free, yeah. Mm-hmm. But if you kill sufficiently many nilpotents, it becomes locally free. For example, you can kill all the nilpotents, then it's certainly locally free. You just get the classical case of algebraic varieties that we covered last year. But there is some intermediate ideal. Well, there is some maximal ideal with this property. So when you kill this ideal, it becomes locally free over the quotient. Okay, so So now we defined those ideals, and there are infinitely many such ideals. But now we set I is the sum of all these ideals. Okay, and a priori this is infinite sum, but since our rings are Noetherian, this is actually a finely generated ideal. The sum is actually finite. And so this ideal sheaf is a coherent sheaf, and it defines a closed subscheme SF. I mean, in WF with the same support. And with the universal property that the direct image of our sheaf is locally free of rank f of n plus I after restriction to SF. Okay, so well, we proved our theorem point 1. If you still remember what was point 1, now it's proved. But now we have to prove 2 and 3. Huh? Just that's how we constructed them. So yeah, for each I, so this ideal contains all those ideals. So the quotient modulo of this ideal factors through all those quotients, and for all of them, the corresponding sheaves were locally free. And so when I pull back to this quotient, it's still locally free. When I pull back a locally free sheaf, it's still locally free.
So
yes.
This universal property for n equals 0 we proved 1, and now we need to prove universal property for n bigger than 0.
Yes. Okay. So we're proving 2, and to this end, recall our very first lemma. This very first lemma was base change for sheaves on projective spaces after high enough twist. Yeah, and in this case, it says that there is some n prime bigger than this n, such that for any twist higher than n prime, the push forward of twisted sheaf restricted to SF is isomorphic to the push forward of the well, just the base change. After high enough twist. Now we will also need the next lemma. Next lemma was some condition for local, well, for flatness or local freeness of the direct image. And so it implies that the sheaves restricted to our strata, well, how to say it? Are flat and locally free. Yeah, remember there was a condition that if all the high enough twists are locally free, then the original sheaf is flat. Sorry. Here is just flat. Okay. All those sheaves, so flat over SF, over the strata. Okay. That's fine. And that's already part of part 2. So we know that the pullbacks to the strata are flat. And now we want to prove that the strata are universal with this property. That if pullback somewhere is flat, then it factors through a stratum. Okay. So for the converse property, if we are given a morphism from a test scheme to S, such that the pullback is flat over T, then the Hilbert polynomial of Ft will be a constant, or locally constant. Over T. This we proved that the Euler characteristic is constant in the flat families. Okay, and let Tf be the union of connected components of T, where the Hilbert polynomial equals this particular F. And then the morphism from Tf to S set theoretically factors through SF just by definition. Okay, but we also know that the push forward of restriction of F to T is locally free of rank f of I on TF. Yeah, and hence the actual scheme morphism from TF to S factors through I don't have SF by construction, by definition of our SF. Okay, and this is what we wanted to prove. I think it's SF. Okay, so we only have to check point 3 now, and 3 is immediate. Maybe I can finally erase. Here's point 3 that we need to prove. Oops.
SF closed, that's a closure of SF should lie.
Right. Sorry, yes, thank you. Closure, yes, thank you. Yeah. So, note that the same order is given by comparing just one particular value, f of whatever, capital R, bigger g of capital R, for, well, how to say, just one capital R big enough. If you just think of what is written here, you don't need to compare everywhere. If you already know this, then it suffices to compare just one particular big number. Okay. So now this 3. Yes.
What do we know?
Pardon me?
Check. You said that if you already know this, we only check for large.
For just one number R, yes.
If you already know this, we know what is the greater than 1.
Yes. But you don't have to check for all big numbers, just for one big number. That's what I say.
And how do you know that it is big enough that you can check in it?
Well, it's none of our business.
We can choose for there are finite number of variables, so we can.
Yeah, we don't care for some explicit. It's an interesting problem. I agree, but so far we just don't deal with it.
Okay.
In principle, it's interesting, to find some particular R with this property, but we ignore this problem so far. Okay, and now 3 follows from what already proved n equals 0, and the sheaf E equals just this particular twist. Then we know, we discussed this last Tuesday, right? For just one sheaf, its fibers can only jump, and that's what is claimed here. Okay, so this big theorem is proved, and accept my congratulations. But unfortunately, yes.
I think we started the proof with the case using the case of n equals 0.
But we proved it. We proved n equals 0, and then we somehow reduced general case to this. Just we considered all the direct images of twists, of all the possible twists, and applied n equals 0 case to those twists. And the problem was somehow that there are infinitely many twists, but to obtain a finite certification, you need to use only finitely many of them, and that's what we achieved. Okay, so now finally we can formulate this great Grothendieck theorem about existence of quad schemes, and then next time we'll prove it. Well, maybe we'll start today and finish next time. Rather general formulation of Grothendieck theorem. On quad schemes. So it's more general than what I formulated last week. We have a base scheme S. And so in most applications, this S is just the spectrum of our ground field. So in whatever applications we will encounter, at least, it will be just a point. But still, you can formulate it much more generally over arbitrary base. And there is a vector bundle nu S over S. And again, it can be trivial. And over a point, it has no other choice. It must be trivial. But it can be arbitrary vector bundle. And then we have the projectivization of this vector bundle. And inside we have a closed subvariety X. So it's, in a sense, projective over S, but in this particular sense. Maybe when we usually write that X lies in P and S, then we assume that our vector bundle is trivial. But it can be non-trivial. Okay. So now we also have a coherent sheaf E. Maybe we'd rather assume that this coherent sheaf is a quotient of some other vector bundle. So E is a quotient of the pullback of some other vector bundle from S, and it can be also twisted by something. So WS, a vector bundle on S, and nu is an integer. Okay, And again, this vector bundle can be taken trivial. So it can be equal to OS of mu to the power whatever m prime. Okay, so these are some initial data, and to these initial data we associate some functor, the quad functor, and then I will formulate that it's representable. So maybe also fix a Hilbert polynomial phi, just any integral valued polynomial, numerical polynomial. So the quad functor it depends on E, this coherent sheaf, well, maybe over X over S. Also, it depends on the Hilbert polynomial and also on the line bundle L. It's a relatively very ample line bundle on X. So for example, L can be taken just OP of Vs of 1 restricted to X. Restricted to X.
Does it mean to be very ample? But this vector bundle is not.
It's relatively very ample. Well, for example, it's very ample restricted to any fiber. Okay. Or very ample restricted to any affine subscheme in S, whatever. So I think it's clear, but this is the most general formulation.
This line bundle on what?
On X.
X is over S.
Yes, certainly. And S, just in all applications we are concerned with, S will be just a point.
Okay. Fibers are some projective varieties.
Yes.
L restricted to fibers is
Very ample. Yes.
X is a projective variety.
Yes.
Why do you write it in brackets?
Well, because in our previous more restrictive terminology, I only considered projectivizations of trivial vector bundles, just the direct product, so to say. Well, if you are over base field, then it's direct product. If as a spectrum Z, then I cannot say that it's direct product, but it's just projectivization of trivial vector bundle. But it can be more general. It can be non-trivial.
You mean say projective? It is incorrect.
No, it is correct, but you have to assign some meaning to the word projective, and there are various levels of projectivity. There is some trivial projectivity or some variable projectivity. It's just the most general statement, but again, in our applications, it's all very down to earth. To begin with, the base scheme is just a point, and so there is no difference between trivial and non-trivial vector bundles.
Is it the most general formulation?
Yes, this is the most general formulation. Yes, up to date.
The Grotnik himself
gave it in this formulation. Yes. So if you have a test scheme T over S, then the value of this functor is the set of pairs F and Q, where F is a coherent sheaf on X, and Q is the quotient morphism from E. It's on the base change to T, and this also to Ft, to the base change to T. Okay.
Что там стоит? F лежит в девятых точках.
Yes. So, well, you have P of Vs over S. Well, okay, and there is a morphism T here. Well, there is also X inside here, and so you can pull it back and get XT over T. And xt also will live in projectivization of Vt. Yeah. Just the base change, the Cartesian product. Yeah. And then you're given some quotient sheaf of, sorry, again, Et. So to pull back everything to T, and you consider such a quotient. Huh?
We don't need Ft because F is coherent over X.
It's here, yeah, here and now. Yeah, sorry. Yeah. Mm-hmm. But maybe rather I should put it here, yeah, like this. Yeah. Okay, so this is some set, and
E is some fixed.
E is fixed, yeah, but it has to be.
How is it defined in the case S is a point? It is a quotient of.
Then there is no problem because any coherent sheaf over project space can be represented like this. It's a quotient of some vector bundle.
S is a vector bundle.
Yes.
On a point.
So it's just a vector space, and you just twist sufficiently your vector space, and then it will cover any coherent sheaf. Because any coherent sheaf sufficiently twisted is generated by its global sections. We proved this last year, and if you untwist, you get this claim that it's a quotient of something like that.
For each E, there exists such WS with such a.
Over a point, yes. Over a point, there is nothing to require. But if S is some big scheme,
For every E, there exists such W.
yes. Over a when S is a point, this requirement is redundant. You don't need to ask this. This is automatically true for big enough nu. And if S is not a point, then you'd rather require this.
And also here we, I think, have to use the Hilbert polynomial.
Right, absolutely. Absolutely, so that the Hilbert polynomial, well, the Euler characteristic of Ft of R is equal to phi of R for any t.
And for R means that we twist by.
Yes.
T.
Right. By this guy, L. Absolutely. Mm-hmm. Yes, thank you. Mm-hmm.
L
T over capital T in the index.
Capital T in the index
F.
of F.
With a
No, I take all the fibers. All the fibers.
Okay,
L is very ample.
L is relatively very ample, yes.
S is a point very ample. Just
Yes, absolutely, yes. Mm-hmm. Fine. I mean, if our X is just the whole project space, then there is nothing to speak about. But if X is just a projective variety, for example, an elliptic curve, yeah, or some higher genus curve, then there are very many different very ample line bundles. And for any of them, you can speak of Hilbert polynomial in this sense, with respect to this particular very ample line bundle, okay? So you'd rather have this generality. Okay? But if X is the whole project space, then it's just O of 1 over n. So this is the definition of the functor we're after. And it goes to sets because there are no automorphisms, because this sheaf E is fixed, and F is the quotient of this fixed E. That's the rigidity in our problem. And there are no automorphisms of this. Because we are considering not just abstract sheaves F, but F realized as quotients of E.
It's rigid because we consider pairs.
Yes, because Q is part of data. So we can have, well, various isomorphic quotients F, but they will be different elements of this set if the projections are different. Okay? And in this formulation, there are no automorphisms. And that's why we get into sets, not into groupoids. And that's why there is a chance that this thing will be represented by a scheme, not by a stack. And that's what actually happens. So there is a theorem by Grothendieck. But the proof we will give next time will be somewhat shorter and more elegant version given by Mumford, like 5 years later, that this functor is representable by a scheme. Well, that is called quad scheme without underline. Okay.
And why are you taking out the close points T? It's not all the points.
Because it's enough. We discussed already that you may also consider all the points, but then you will not have any new Hilbert polynomials. They will be just.
Because the general point,
Generic point is the same. Yeah. Mm-hmm. Yes. Okay. So well, I will not have time for anything else, but still, let me formulate some lemma. Next time it's very straightforward, so it will take us just 2 minutes to prove it next time. Still, let me formulate it now, and then recall it next time. Some trivial reduction. So it suffices to consider. By the way, I'm sorry. Before I erase anything here. Yeah. Sorry, I forgot even to formulate the theorem. So it's represented by a scheme, and this scheme is projective. So maybe let me continue here. I'm sorry. This quad scheme is projective in the sense that it's a closed subscheme in the projectivization of some vector bundle. We had V, we had W, so it's like U. Yes? And if V and W are trivial, then US is also trivial. Okay, so if we consider the most straightforward notion of projectivity in the statement, then in the answer we also get projectivity in the same most straightforward manner. So it's important. The important thing that it's projective, not affine or anything, but closed, proper, projective. So I wanted to say that it suffices to consider X equal to the ambient projective space and E equal to the just vector bundle pulled back from S. Okay, in principle we considered some quotient and some closed subscheme, but it doesn't matter just because you can the quotients of this sort, there are a fortiori quotients of that sort. Okay, because X is a closed subscheme of project space, so you can realize any coherent sheaf on this subscheme as a quotient of some vector bundle on the ambient project space. So we'll prove this. Well, I will formulate a lemma and prove it next time, and then we'll continue under these assumptions. And next time we'll prove the Grothendieck theorem. Okay, thank you. Sorry for.
If X is just a projective space,
Yes.
then this is very clear, very stupid function.
No, I don't say this. No, I just said that there are various notions of projectivity. One projectivity is just projectivization of trivial vector bundle, another one projectivization of arbitrary vector bundle.
I mean, if X is just the ambient space.
Yeah, then the most general statement is very easily, immediately reduced to this statement, but in this case, it requires the whole machinery we developed. So it's easy to reduce to this particular case, but to prove it in this case will require everything we worked out so far. And then, so next Tuesday we will prove this theorem, and next Thursday we will consider some particular, very, very particular case when the Hilbert polynomial is a constant. So it's like a Hilbert scheme of points. These points can merge together into points with nilpotents, but nothing more interesting. And still, in this case, it's already very interesting. But by the way, this resulting quad scheme, in general, is very, very bad. Even if you start with S, just a point, and even if you consider constant Hilbert polynomials, like for a few points, like 3 points, and the project space like just P3 also, just P3 and over a point, and just 3 points. This Hilbert scheme, this quad or Hilbert scheme will already have nilpotents and will be non-smooth. So in general, it's very, very bad.
And is this object a motivation to study schemes?
Yeah, for example, this very natural functor is represented by a scheme that usually has nilpotents and is non-smooth, and well, it's just a very bad general scheme.
So Hilbert scheme classified varieties, but you can't classify variety with variety. You need schemes.
Yes, you do need schemes. Mm-hmm. Okay. So like there are some sub-schemes that can be deformed infinitesimally, but not actually deformed. And the same is true for Picard functors in general, like already on a surface. And at the time Mumford worked out this better proof. He wrote the whole book, lectures on curves on a surface, about this Picard problem and its complications.
What's the Picard problem again?
Well, classification of line bundles, so to say. but again, in general, well, for curves, it's an abelian variety, smooth and very nice. But for surface already, it can be very bad.
For smooth surfaces, it should quite be.
For smooth surface, yes, but still, it will have nilpotence. Yeah.
You say that you cannot report.
Yes.
You
But what are nilpotents? It's like dual numbers. It means that, well, you know that morphisms from dual numbers to x is just sort of a tangent bundle to x. So, well, there is just one point here, but it's a thick point, so to say. And this particular point goes to x, but this thickening goes to the tangent vector. But well, it is very general, yes. But if x itself has nilpotence, then it may happen that it has a thick point also, like this. And it means that there will be some non-zero tangent vector, but there are no actual points to go to move to. Okay, so there are infinitesimal deformations, but they are not integrable. Just there is no place to move. Okay? And that's what actually happens if you consider the moduli scheme of.
I mean, you say you can consider the space of infinitesimal deformations.
Yes.
And you claim something about this space.
Yes.
What is the claim?
That your tangent space can be high dimensional, but the variety itself may be low dimensional, for example, zero dimensional. The tangent space can be arbitrarily high dimensional, but the space itself can be arbitrarily low dimensional. So it means that the infinitesimal deformations do not integrate.
You mean there is some abstractions?
There are some higher abstractions, yes.
Is there some cohomology
Yes.
group?
Yes. So if you apply it to such a scheme, since it classifies families of quotients or subschemes, for example, then it means that there are some bad subschemes in the ambient projective space, such that they are infinitesimally deformable, but not globally. You cannot actually deform them, but infinitesimally you can.
How is it connected to what we discussed? Yeah, I understood that it was a tangent space of big dimension.
Yeah, so it can happen that the tangent space is big, but the space itself is small. So there are infinitesimal deformations. The points of quarter Hilbert scheme are represented by some subschemes, for example, in case of Hilbert scheme. So you can think of a point here as a subscheme in project space. And then the fact that this space has few points, like just say 1 point, means that this subscheme cannot be really deformed. But the fact that it has many infinitesimal deformations means that infinitesimally it can be deformed. So over dual numbers, there are close subschemes, but in reality, there are no other subschemes. That's what you see.
Will we consider more touchable examples?
No. I plan to consider only point schemes on whatever, on the plane, and there the Hilbert scheme will be smooth. So nothing like this will happen. But if you consider a random example, then Hilbert scheme will be very bad. Never smooth and always with nilpotence. I have to specifically prepare examples when it's good. And this is one example when it's good. But if you consider just point subschemes in higher dimensions, A3 for example, then it will be already bad. Non-smooth with nilpotence. Thank you.